planet where rock falls from the sky is not supposed to exist. But on K2-141b, it is simply weather. The world completes an entire orbit around its star in 6.7 hours. While you slept last night, this planet went around its sun more than once. Its day side reaches approximately 5,400 degrees Fahrenheit, hot enough to melt rock and push some of its minerals into the atmosphere as vapor, and there is no night to cool it. K2-141b is tidally locked, meaning the same side has faced its star continuously for billions of years. One hemisphere remains trapped beneath permanent daylight, while the opposite side exists in perpetual darkness. The difference between them is almost impossible to comprehend. The day side reaches 5,400 degrees Fahrenheit. The night side falls to approximately minus 330 degrees Fahrenheit, colder than Pluto, and separating these two extremes is only a few hundred miles. Between them, winds race at more than 3,900 miles per hour. Rock vapor rises from the molten surface, gets carried toward the darkness, cools, condenses, and falls back toward the planet as molten minerals. Then the cycle begins again, every hour, every day, for billions of years. And this is not science fiction. K2-141b is a real rocky planet approximately 202 light years from Earth, and scientists have been able to reconstruct its terrifying weather from the faint changes in light that reach our telescopes. The deeper they model it, the stranger it becomes, because beneath all that violence is a planet made from the same fundamental materials as Earth: iron, silicates, rock, a world that should feel familiar, subjected to conditions so extreme that its entire surface behaves like a global furnace, and its atmosphere becomes part of a planetary rock cycle, unlike anything found in our solar system. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. It starts with the side of K2-141b, where the ground itself begins to boil. The first clue came from a pattern repeating with remarkable precision. Every 6 hours and 42 minutes, the light of K2-141 star dipped slightly, then returned to normal. Something was crossing the star again and again, following an orbit so short that several of these events could occur within a single Earth day. In 2017, astronomers connected those repeated dips to a planet now known as K2-141b. The discovery came through transit photometry, a method that measures the tiny change in a star's brightness when a planet passes across its face. We cannot see the planet directly in these observations. Instead, we watch its shadow move across starlight, and from that recurring signature, its existence becomes measurable. The telescope responsible was part of the National Aeronautics and Space Administration's K2 mission, an unexpected continuation of the Kepler Space Telescope after two of its stabilizing reaction wheels failed. Engineers found a way to keep the spacecraft useful, and that extended mission opened another window onto planets orbiting distant stars. What emerged was larger than Earth, but still unmistakably rocky. K2-141b has a radius about 1.5 times Earth's, while its mass is about 5 times greater. Its density is roughly 8.2 grams per cubic centimeter, indicating a world dominated by iron and silicate rock, rather than a deep envelope of gas or water. The planet lies about 202 light years away, toward the constellation Aquarius. That distance places it far beyond any practical journey, yet its host star is bright enough for astronomers to extract unusually detailed information. K2-141 itself is a K-type dwarf, somewhat smaller and cooler than our Sun. Distance from the star changes everything. K2-141b circles its host at only about 820,000 miles, placing it roughly 44 times closer to its star than Mercury is to the Sun. At that range, orbital motion becomes extraordinarily fast. One complete revolution takes only 6.7 hours. Worlds with these ultra short periods have become increasingly common in exoplanet surveys, revealing a planetary environment with no true counterpart in our solar system. They occupy orbits so close to their stars that ordinary ideas about weather, geology, and planetary survival begin to stretch. K2-141b has become especially valuable because several measurements reinforce one another. Its size, mass, density, orbital timing, and relatively accessible star allow researchers to test detailed models against the same world repeatedly. For scientists studying molten rocky planets, it has become a benchmark. And that leaves us with a remarkable physical problem. A planet built from familiar ingredients has been placed in an unfamiliar furnace, close enough to its star that its entire planetary system becomes an experiment in extreme planetary physics. A useful way to picture K2-141b begins with its rotation. Imagine standing on one location and watching the star hold the same position overhead, day after day, while the ground beneath you turns once during every orbit. On this world, the orbital period and the rotation period are synchronized at 6.7 hours. That condition is called tidal locking. Gravity creates it through a subtle imbalance. The star pulls slightly harder on the planet's near side than its far side, stretching the planet along the direction of the star's pull. As K2-141b rotates, that uneven gravitational force produces a torque, a twisting influence that removes rotational energy over time. For a young planet, the process begins gradually. Each cycle carries a tiny amount of energy away from the planet's spin until the rotation settles into synchronization with the orbit. The final state is remarkably stable. One rotation now takes exactly as long as one revolution, keeping the same hemisphere turned toward the star. We have a familiar example much closer to home. The moon is also tidally locked, which is why one lunar hemisphere has always faced Earth. But the comparison has an important limit. The moon circles Earth, while Earth continues traveling around the sun, so sunlight still moves across the lunar surface during each lunar cycle. K2-141b has no such second motion to restore a conventional day. Its star is the body controlling the lock, and the planet's orientation remains fixed toward it. If you stood there, the star would occupy a nearly permanent place in your sky. The geometry becomes stranger when the planet's closeness to its star is considered. Because the star appears large across K2-141b's sky, the region receiving direct illumination extends beyond the simple half of a sphere we might expect. Roughly two-thirds of the surface can remain exposed to direct starlight, leaving about one-third without it. Between these regions lies the terminator, the boundary separating illuminated ground from permanent night. It is not a narrow strip of gentle twilight. Across a planetary distance measured in only a few hundred miles, the amount of incoming energy changes enormously. For us, that means rotation is no longer redistributing heat around the globe. The same regions remain exposed to the same stellar geometry, while other regions remain turned away. Over immense stretches of time, that persistent arrangement allows each side to develop its own physical conditions, with no ordinary sunrise or sunset interrupting the pattern. For you, there would be no changing horizon of light to mark the passage of another day. Tidal locking, then, is more than a peculiar orbital state. It is the mechanism that fixes the planet's geography of illumination, giving every later process a permanent stage on which to operate. A strange boundary disappears across the day side of K2-141b. At these temperatures, the distinction between ground and ocean loses its meaning because the surface itself has become fluid. The dayside reaches approximately 5,400 degrees Fahrenheit, far beyond the melting points of the minerals that build rocky planets. Olivine melts near 2,900 degrees Fahrenheit, pyroxene near 2,500, and feldspar around 2,200. Those minerals do not merely appear in isolated pools. Models indicate that the illuminated hemisphere is covered by a continuous magma ocean with molten rock extending roughly 62 miles beneath the surface. The depth comes from calculations of how heat moves through the planet, constrained by its measured properties and the intense stellar energy arriving overhead. Beneath that molten layer, conditions change. The star's energy does not reach deeply enough to liquefy the entire planet, leaving a solid interior below the magma ocean. We can therefore picture K2-141b as layered by temperature, with a fluid surface surrounding a much colder interior. Yet the magma ocean itself is far from motionless. Heat drives convection, meaning hotter material rises while cooler material sinks. On Earth, similar circulation moves slowly through the mantle. Here, the material undergoing that motion is already liquid. At the point directly beneath the star, another physical boundary begins to disappear. The surface becomes hot enough for molten minerals to enter the gas phase, turning portions of the magma ocean into vapor. This evaporation is governed by the same thermodynamics that controls boiling anywhere else. Add enough energy, and molecules escape the liquid surface. On K2-141b, the energy source is relentless stellar radiation concentrated onto a planet that cannot rotate its surface away from the star. You can imagine the transition occurring across the day side as a gradual change in state. Farther from the hottest region, molten rock remains the dominant surface condition. Closer to the substellar point, evaporation becomes increasingly important, feeding material upward into the atmosphere. That creates an unusual planetary boundary. The surface can exist as solid material below, liquid rock above it, and vapor rising from its hottest regions, all within one connected system. The boundary between those states is constantly shifting as heat moves through the surface. For us, the familiar categories of land, sea, and sky begin to overlap. Here, the surface itself supplies the atmosphere, while the atmosphere can return material to the surface in another form. K 2141b is therefore not simply a planet with lava on it. Its dayside has become a place where the basic states of rocky matter continuously exchange with one another. Beneath the molten surface, K2-141b may resemble a familiar planet more than its appearance suggests. Its measured density points toward a world built from the same broad ingredients that shaped Earth, with heavy metal concentrated toward the center and silicate rock surrounding it. The density is roughly 512 pounds per cubic foot. That value places important limits on what can exist inside the planet, because a world filled mainly with lighter materials would be far less massive for its size. The simplest interior model, therefore, contains a substantial iron core beneath a thick silicate mantle. Pressure changes the behavior of that iron dramatically. Deep inside the planet, immense compression can keep iron solid even at temperatures far beyond anything found naturally near Earth's surface. Higher above the deepest region, pressure decreases, allowing part of the core to remain liquid. That distinction matters for magnetism. On Earth, moving liquid iron in the outer core generates our planetary magnetic field through a process called the dynamo effect. Convection and rotation organize electrically, conducting material into currents, producing a magnetic field that extends far beyond the surface. Whether K2-141b operates a similar dynamo remains uncertain. Its rotation is synchronized with an orbit lasting only 6.7 hours, and its interior may have conditions capable of sustaining some magnetic activity. Yet mass and radius measurements alone cannot reveal whether the core is sufficiently fluid, convective, and electrically active. If the planet possesses only a weak magnetic field, its upper atmosphere would have less protection from charged particles arriving from its star. Those particles form a stellar wind, a continuous stream of electrically charged matter flowing outward from the stellar surface. The consequences reach deep into the planet's atmospheric history. A vulnerable atmosphere can lose particles into space, especially when intense radiation and stellar wind act together over geological timescales. For a world already generating gases from its surface, atmospheric survival becomes a balance between continual replenishment and continual escape. Farther down, the silicate mantle forms another immense layer. Unlike the molten material above it, much of this rock remains solid under pressure. Yet solid does not mean motionless. Over millions of years, heat can drive extremely slow convection, allowing material deep within the mantle to rise while cooler material descends. Earth uses similar internal circulation to redistribute heat and shape its surface. Whether K2-141b developed anything resembling terrestrial plate tectonics is much harder to determine. The immense molten layer above the mantle could alter how stresses reach the surface, changing the relationship between interior motion and crustal movement. At roughly 62 miles beneath the surface, the character of the material changes again. This depth marks the mottled boundary where the molten silicate layer gives way to solid mantle beneath it. There is no sudden change in chemical identity at that boundary. The same broad mineral ingredients can occupy both regions, while temperature and pressure determine whether they remain liquid or solid. Deep beneath the incandescent surface, the planet therefore contains a layered interior whose structure is governed by the same fundamental physics that operates inside Earth, only under conditions far more extreme. For most rocky planets, the atmosphere begins with material rising from within. Volcanoes release gases, oceans add vapor, and chemical reactions continually reshape the mixture above the surface. K2-141b follows a very different path because its atmosphere is being produced directly from the planet's molten exterior. Any original atmosphere would have faced an unforgiving beginning. Light gases, such as hydrogen and helium, could not remain for long under the combined effects of intense stellar radiation and the powerful stream of charged particles flowing from the star. Over the first several 100 million years, those gases were likely stripped away and carried into space. What remains is stranger. The atmosphere can form from the rock itself. At the hottest regions, minerals within the magma ocean receive enough energy to escape into the gaseous state. Sodium is especially important because it vaporizes more readily than many heavier silicate compounds. Farther toward the cooler portions of the dayside, sodium can therefore become increasingly prominent in the thin layer above the surface. Closer to the hottest central region, silicon monoxide and silicon dioxide become important. These substances are familiar to us in solid form because silicon compounds make up much of Earth's crust, sand, and glass. Here, under extraordinary temperatures, the same ingredients exist as vapor rising directly from molten rock. The result is a rock vapor atmosphere. It is extremely tenuous compared with Earth's atmosphere, yet its small amount of material does something important. It provides a pathway for minerals to leave the surface, move through the upper layers, and eventually encounter dramatically different conditions elsewhere. The atmosphere also has a distinctly uneven distribution. It is densest above the hottest parts of the dayside, where evaporation continuously supplies fresh material. Moving outward toward the terminator, temperatures fall and the supply of vapor changes. Beyond that boundary, conditions become increasingly hostile to keeping these minerals suspended as gas. For you, the remarkable part is how little separates the surface from the atmosphere. On Earth, the solid ground beneath our feet and the gases above us belong to visibly different environments. Here, the distinction is constantly being crossed. A portion of the molten surface can become vapor, rise above the planet, and later return as condensed mineral material. Scientists had predicted this possibility before detailed observations of lava worlds became available. The idea follows naturally from thermodynamics because sufficiently intense heating must eventually drive surface minerals into the gas phase. K2-141b became especially valuable because its measured properties allowed researchers to construct detailed models of this process. Those models could specify which minerals should dominate at different temperatures, where the vapor should be concentrated, and how its distribution might influence observable light. That makes the atmosphere more than a thin shell surrounding the planet. It is a direct expression of the surface itself, continuously renewed by evaporation and governed by the changing temperature across the dayside. The air above this world is, in a very literal sense, part of the planet becoming atmosphere. Weather on K2-141b has no familiar rhythm. There are no passing fronts, changing seasons, or storms moving across a rotating globe. Instead, the atmosphere follows a persistent path created by an enormous difference in temperature between the planet's two hemispheres. Air moves when pressure differs from one place to another. On Earth, sunlight warms some regions more than others, creating pressure gradients that drive winds across continents and oceans. K2-141b takes this process to another scale, with thousands of degrees separating regions only a few hundred miles apart. The hottest regions heat the thin rock vapor above them, causing that gas to expand and rise. Farther away, cooler material produces different pressure conditions. The resulting circulation sends atmospheric material away from the intensely heated dayside and toward the colder hemisphere. Models indicate that these winds can exceed 3,900 miles per hour. A commercial aircraft typically travels at roughly 575 miles per hour, making these atmospheric currents several times faster than a passenger jet. They are also supersonic. At Earth's sea level, sound travels through air at roughly 767 miles per hour. On K2-141b, the modeled mineral winds can move far beyond that threshold, carrying sodium and silicon compounds across the planetary atmosphere. For you, the important detail is what those winds are transporting. This is not ordinary air moving over a rocky landscape. The flow contains material that was recently part of the planet's surface, lifted into the atmosphere after intense heating. As the current approaches the terminator, the thermal environment changes rapidly. The gas encounters progressively colder conditions, altering its density, pressure, and ability to remain suspended. Higher layers can behave differently from regions closer to the surface, creating atmospheric circulation that varies with altitude. That layered structure matters because wind speed is not necessarily uniform throughout the atmosphere. Temperature changes with height, while radiation deposits energy differently at different levels. The result is a complex flow field, with separate regions of motion interacting across the thin atmosphere. There is enormous mechanical energy in this circulation. The moving gas carries heat away from the regions receiving the greatest stellar input, while simultaneously transporting mineral material toward colder territory. We can think of the atmosphere as the planet's great conveyor. Surface material enters the gas phase. Atmospheric motion carries it across vast distances, and changing temperatures eventually force that material toward another state. The circulation, therefore, connects regions that would otherwise evolve almost independently. Heat moves outward, minerals travel with it. Every hour, the atmosphere performs this transfer again, driven by the permanent contrast established across K2-141b. The journey of mineral vapor changes character at the terminator. As the heated atmosphere moves away from the day side, its temperature begins to fall, and gases that once floated above molten rock can no longer remain suspended. Condensation begins. This is the same basic physical process that gives us rain on Earth. Water vapor cools, becomes liquid droplets, and eventually falls under gravity. On K2-141b, the substance moving through the atmosphere is fundamentally different. Sodium and silicon compounds can leave the surface as vapor, then condense into solid mineral particles when temperatures become low enough. Those particles have nowhere to remain aloft. Gravity takes over. Instead of droplets striking a surface, mineral grains descend toward the permanently dark hemisphere. The predicted precipitation could resemble a dense fall of fine dust, with countless particles settling onto the frozen ground over immense spans of time. Different minerals should condense at different temperatures. Sodium, being more volatile, can solidify closer to the boundary between the illuminated and unilluminated regions. Silicon dioxide requires colder conditions, allowing its deposits to form farther across the night side. That separation could leave the surface chemically organized. Imagine moving across the night side and crossing regions where one mineral gradually gives way to another, each zone marking a different stage in the cooling of material carried from the day side. We would be looking at weather written into geology. Every layer could preserve something about the atmospheric conditions that existed when it formed, creating a physical record of how heat and material move across the planet. Over time, these deposits may become remarkably substantial. Models have described the accumulated material as rocky glaciers, although there is no water ice involved. Instead, gravity and continued deposition can compress and mobilize mineral matter across the surface. The process does not necessarily end where the particles settle. As deposits grow, gravity can encourage surface material to flow toward lower regions and eventually back toward the hotter hemisphere. That creates a planetary circulation extending beyond the atmosphere. Material leaves the molten surface as vapor, travels through the atmosphere, condenses into mineral grains, accumulates across the night side, and can eventually move across the surface again. The timescale of each stage differs dramatically. Atmospheric transport can occur rapidly, while the accumulation and movement of solid deposits unfold over much longer periods. Yet the underlying cycle remains connected. For you, the remarkable detail is that the rain does not require clouds, no water droplets are needed, and no familiar storm system has to form. The essential ingredients are temperature, pressure, gravity, and material capable of changing state. Scientists have not watched this mineral precipitation directly. It remains a prediction derived from atmospheric and thermal models of K2-141b. But the physics behind condensation is well established, and the planet provides an extraordinary environment in which those familiar laws can operate with molten rock as their source material. Across the night side, every falling grain would represent another small transfer of matter, carrying a fragment of the dayside's heat driven chemistry into the planet's colder half. A planet can reshape itself without a single continent moving. On K2-141b, the material forming the surface is constantly changing location and state, creating a planetary cycle powered almost entirely by heat. The process begins when exposed minerals leave the magma ocean as vapor. Once airborne, that material becomes part of the atmospheric circulation, traveling away from the intensely heated regions toward the colder hemisphere. There, the temperature falls enough for vapor to condense into solid grains. Gravity draws those particles downward, building deposits across the night side. Layer after layer can accumulate. But the material does not necessarily remain there forever. As deposits grow, gravity can drive surface movement toward lower regions, gradually carrying mineral matter back toward the hotter hemisphere. Eventually, some of that material can reach the magma ocean again, where intense heating returns it to vapor. The complete circuit therefore links surface, atmosphere, and nightside terrain. Evaporation removes material from one region, atmospheric transport carries it across the planet, condensation deposits it elsewhere, and surface flow can return it to its origin. Earth has a rock cycle too, although its machinery is different. Our rocks are weathered, buried, altered, melted, and eventually returned through geological processes that can require millions of years. K2-141b achieves a comparable exchange through temperature-driven evaporation and atmospheric transport. The timescale is especially striking. Mineral vapor can cross the planet's atmosphere in only hours, meaning one stage of the planetary cycle operates faster than an ordinary workday. The surface response is slower, unfolding across much longer intervals as deposits accumulate and migrate. Whether the entire system has reached a perfect balance remains uncertain. Scientists cannot yet determine whether the night side receives exactly as much material as eventually leaves it, or whether one hemisphere is gradually gaining mass while the other loses it. That uncertainty matters because the cycle may be changing the planet's surface over geological time. A small imbalance, repeated countless times, can become significant when given millions or billions of years. We can therefore think of K2-141b as a world continually moving its own ingredients around. The dayside supplies material to the atmosphere delivers it to colder ground, and gravity begins the return journey. Nothing in this exchange requires oceans, rainfall, rivers, or conventional plate tectonics. The driving force is simply the enormous contrast between different parts of the planet, turning heat into motion and motion into geological change. Across immense stretches of time, the same atoms may pass repeatedly through molten rock, vapor, mineral deposits, and surface flows. The planet is continually rearranging itself, with its atmosphere serving as the bridge between worlds of radically different temperature. Venus gives us one of the clearest starting points for comparison. Its surface reaches roughly 900 degrees Fahrenheit, hot enough to melt lead under the right conditions. Yet even that familiar planetary furnace is less than 1/6 as hot as K2-141b's dayside. Io offers another reference point. The volcanic moon of Jupiter is the most volcanically active world in our solar system, with temperatures near its hottest volcanic vents reaching around 3,000 degrees Fahrenheit. Those eruptions can melt rock across enormous regions. K2-141b still operates at a completely different thermal level. Mercury brings the comparison closer to the Sunday. Its sunlit surface can reach about 800 degrees Fahrenheit, despite being the innermost planet of our solar system. On K2-141b, the average dayside temperature approaches 5,400 degrees Fahrenheit. The difference is so large that Mercury's hottest terrain begins to seem almost temperate by comparison. Then we reach the Sun itself. The visible surface of the Sun is around 10,000 degrees Fahrenheit. K2-141b's dayside reaches more than half that temperature, despite being a solid planet rather than a star. The distinction matters. We are looking at a rocky surface operating within a thermal range usually associated with stellar environments. Earth's volcanic systems provide another useful boundary. Some of our hottest accessible magma reaches roughly 2,200 degrees Fahrenheit. That is enough to melt many minerals found in ordinary rocks. Yet, even this extreme terrestrial material remains far below the temperature measured across K2-141b's dayside. The contrast becomes even sharper when we leave temperature behind and consider wind. Earth's strongest recorded natural wind gust reached 253 miles per hour during Typhoon Olivia in 1996. That was an extraordinary event by terrestrial standards. On K2-141b, modeled atmospheric winds can exceed 3,900 miles per hour. Imagine that difference for a moment. The fastest winds we experience on Earth occupy only a fraction of the speeds predicted for this distant world. There, atmospheric motion becomes fast enough to carry vaporized minerals across the planet before they have time to settle where they began. Even the temperature difference across K2-141b resists familiar comparison. The dayside can approach 5,400 degrees Fahrenheit, while the nightside falls to roughly minus 330 degrees Fahrenheit. The resulting swing approaches 5,700 degrees Fahrenheit across a single world. You could place Venus, Mercury, Io, Earth's hottest volcanic environments, and the Sun into the same mental scale, yet the comparison keeps breaking apart. Each represents an extreme within a familiar category. K2-141b combines those extremes in one place, where heat, atmospheric motion, and planetary geology operate together at conditions rarely encountered anywhere else in our planetary neighborhood. There is something unusual about studying a world we can never visit. Every measurement begins with light, crossing an immense distance before reaching a detector on Earth. From that faint signal, astronomers reconstruct properties that cannot be seen directly. The first layer comes from the planet's transit. Each time K2-141b passes between us and its star, the starlight falls by a tiny amount. The depth of that dip reveals how much of the star's visible surface the planet blocks. Repeating the measurement allows researchers to determine the planet's radius with remarkable precision, narrowing it to about 1.5 times the radius of Earth. Mass requires a different clue. As the planet orbits, its gravity tugs on its star, making the star move slightly toward and away from us. That motion changes the wavelength of the star's light through the Doppler effect. The high-accuracy radial velocity planet searcher for the northern hemisphere measured those shifts, allowing astronomers to estimate the planet's mass at roughly 5 times that of Earth. Once radius and mass are known together, density becomes available. The calculation is simple in principle, because mass divided by volume gives density. The result places K2-141b among rocky worlds, favoring an interior rich in iron and silicate material rather than a thick envelope of gas. Then the planet's heat begins to reveal itself. Observations from the Spitzer Space Telescope measured infrared radiation from the system as K2-141b moved through different orbital positions. By comparing the changing infrared brightness before, during, and after the planet disappeared behind its star, astronomers could estimate temperatures across different regions. That information does something especially valuable. It lets us compare the permanently illuminated hemisphere with the hemisphere turned away from the star. The enormous contrast between them provides clues about how efficiently energy moves across the planet. The same observations also helped test whether an atmosphere might exist. Without some mechanism for transporting heat, the night side should radiate energy away and become even colder. Any measurable redistribution, therefore, places constraints on the material surrounding the planet, even when that atmosphere cannot be sampled directly. You can see the challenge in every number. The planet is roughly 202 light years away, yet tiny changes in brightness can still carry information about its size, mass, temperature, and circulation. Some questions remain beyond what current measurements can settle. The atmosphere's exact composition, the detailed structure of its winds, and the present behavior of its mineral precipitation cycle require stronger observations and more sensitive instruments. We are therefore studying K2-141b through traces rather than photographs. Its light arrives altered by gravity, motion, heat, and chemistry, and each alteration becomes another piece of evidence. Across 202 light years, the planet leaves only the faintest signatures, yet those signatures are enough to reconstruct an astonishingly detailed physical world. The next step in understanding K2-141b depends on separating one faint spectrum from another. The James Webb Space Telescope was built for precisely this kind of problem, with infrared sensitivity far beyond earlier space observatories. Its spectroscopic instruments can spread incoming light into detailed patterns, allowing specific molecules to leave recognizable signatures. Those signatures matter because different substances interact with light differently. Sodium produces a strong spectral feature near 589 nanometers, while silicon monoxide and silicon dioxide produce distinctive features at infrared wavelengths accessible to the telescope. Each absorption or emission feature becomes a chemical clue, revealing what exists above the planet without requiring a spacecraft to approach it. One of the most useful moments arrives when the planet passes behind its star. Before that disappearance, the telescope receives light from both objects. During the eclipse, only the star remains visible. Subtract those two measurements, and the tiny difference represents radiation coming from the planet itself. The signal is extraordinarily small, yet K2-141b offers an unusual advantage. Its orbit lasts only 6.7 hours, so opportunities to observe these eclipses arrive repeatedly. Astronomers can combine measurements from many events, allowing faint patterns to emerge from the noise. With enough observations, individual spectral features become easier to distinguish from instrumental uncertainty and ordinary variations in the star. A detection of sodium, silicon monoxide, or another expected mineral vapor would carry enormous significance. It would provide direct observational support for an atmosphere created from vaporized rock, confirming that material from a molten planetary surface can become part of a measurable gaseous environment. But the absence of a signal would also tell us something important. If the James Webb Space Telescope detects little or no atmospheric signature, the rock vapor may be escaping faster than it can accumulate. Intense stellar radiation and stellar wind could be carrying material away before a substantial atmosphere develops. There is another possibility hidden within repeated observations. An atmosphere may refuse to remain perfectly steady. Earlier observations of other lava worlds, including 55 Cancri E, have suggested atmospheric signals can change over periods ranging from days to weeks. If K2-141b behaves similarly, the atmosphere could be responding to changes beneath its surface. Deep inside the magma ocean, convection continually moves material. Fresh material, rising toward the surface, may contain more easily vaporized elements, creating temporary increases in atmospheric density. Those pulses could leave subtle changes in the planet's spectrum. For you, the remarkable part is where the evidence comes from. A distant world can reveal its atmosphere through a difference barely visible within starlight, repeated across countless measurements. The James Webb Space Telescope turns those tiny changes into a way of reading the chemistry of a planet we can never touch. The night side begins where the light ends. There is no gradual fading into darkness, because the planet's geometry leaves this hemisphere permanently turned away from its star. Temperatures can fall to roughly minus 330 degrees Fahrenheit, creating a surface environment unlike anything found on the planets around our Sunday. Pluto can become colder, depending on location and season, but even that distant world receives sunlight. Here, direct stellar illumination never reaches the ground. The atmosphere changes with the geography. Mineral vapor rising from the day side is carried outward, cooling as it travels toward the terminator. Much of that material condenses before reaching the deeper night side, leaving extremely little gas above the frozen deposits. What remains is a surface built from material that once existed as vapor. Sodium and silicon compounds arrive as condensed mineral particles, settling across older layers and gradually changing the composition of the ground. There are no familiar volcanic landscapes here. The terrain is shaped instead by deposition, compression, and the slow movement of accumulated material. Layer after layer can preserve subtle changes in what the dayside atmosphere carried across the boundary. For you, the strange part is how completely the environment is governed by location. A few hundred miles from this frozen terrain, the same planet presents conditions hot enough to vaporize rock, cross the boundary, and the energy available to the surface falls dramatically. The absence of a substantial atmosphere has another consequence. Sound needs a medium through which pressure waves can travel, and the night side provides almost none. There would be no rushing air overhead, no weather moving across the surface, and no familiar acoustic landscape. Above that frozen ground, the sky would offer a different view of the universe. Without a thick atmosphere to scatter incoming light, distant stars could appear with extraordinary clarity. The Milky Way would stretch across the darkness, while the local star remained hidden beyond the horizon. There would also be no ordinary moonlit glow to soften the terrain. K2-141b has no known moon, and its night side receives essentially no direct light from its star. The mineral plane would therefore be illuminated only by extremely faint sources, leaving the surface dominated by darkness. The physical contrast is extraordinary. On the day side, temperatures near 5,400 degrees Fahrenheit drive rock toward vapor, while winds carry that material across the planetary boundary. On the night side, the same minerals lose energy and settle into frozen deposits. This hemisphere is therefore more than a destination for material leaving the day side. It is where the planet's exported matter becomes part of the surface again, preserving a geological record of everything that has crossed the boundary over immense spans of time. K2-141b. may have begun its history far from the furnace it occupies today. During the earliest stages of its planetary system, solid material could gather within the cooler regions of a vast disk surrounding the young star. That disk contained gas, dust, and countless rocky particles. Gravity slowly brought some of that material together, allowing larger bodies to emerge. K2-141b likely formed under conditions very different from those surrounding it now, when temperatures were low enough for substantial rocky material to remain solid. Then its orbit began to change. A forming planet, embedded within the protoplanetary disk, interacts gravitationally with the material around it. Those interactions can transfer angular momentum between the planet and the disk, gradually shifting the planet's orbit inward. The process is called disk migration, and although it unfolds across millions of years, the accumulated movement can be enormous. For K2-141b, the journey carried it extraordinarily close to its star. Its present orbit lies at only about 0.0088 astronomical units, deep inside the region occupied by Mercury in our own solar system. Mercury remains much farther from the Sun, by comparison, leaving our planetary neighborhood without anything occupying an equivalent orbit. The system itself offers another clue to this complicated history. K2-141 has a companion planet, K2-141c, completing an orbit in roughly 7.7 days. Its properties are consistent with a world in the class of Neptune, suggesting that this planetary system contains both a gas-rich outer planet and a heavily irradiated rocky world. That combination raises a natural question. Did the two planets influence one another while their orbits were changing? Gravitational interactions between neighboring planets can alter orbital paths, eccentricities, and long-term stability. Dynamical astronomers can model these interactions, testing whether K2-141c could have affected the final position of K2-141b. The available evidence does not yet provide a definitive answer. There is another transformation written into the planet's history. When K2-141b first formed, it may have captured lighter gases such as hydrogen and helium from the surrounding disk. Those gases could not survive indefinitely at its eventual location. The young star would have been more active than it is today, producing stronger radiation and a more intense stellar wind. Over the first few 100 million years, those conditions likely stripped away much of the planet's original atmosphere, leaving its surface exposed to the star. What remains is therefore fundamentally different from what the planet may have possessed at birth. Its present atmosphere is generated from the world itself, created as intense heating removes material from the molten surface and sends mineral vapor into the surrounding space. K2-141b is consequently a record of planetary migration written into matter. A world that formed in a comparatively ordinary region of its young system was carried inward over immense stretches of time, losing its original gaseous envelope along the way. By the time its migration ended, the planet had entered an environment where its own surface became the source of its atmosphere. The star above K2-141 is cooler than our Sun, yet distance changes what that difference means. K2-141 belongs to the K-type dwarf class, a family of stars somewhat smaller and cooler than the Sun, but still capable of producing immense energy over extraordinary spans of time. For us, the important detail is not simply the star's temperature, it is how close the planet has moved to it. K2-141b circles at such a small distance that the radiation arriving at its surface overwhelms anything experienced by the planets of our solar system. The star does not need to be hotter than the Sunday. Proximity does the work. K-type dwarfs are especially interesting because they can remain stable for far longer than sun-like stars. Depending on their mass, some may shine steadily for tens of billions of years. That gives K2-141b an unusual stellar environment, one that can persist across geological ages while the planet's surface continually responds to the energy above it. The star also sends something more tangible than light. Stellar wind is a continuous stream of charged particles flowing outward through space. K2-141b receives that flow at extremely close range, where the exposed upper atmosphere can be struck repeatedly by energetic particles. Higher energy radiation adds another layer. Ultraviolet and X ray photons can ionize atoms and molecules in the upper atmosphere, giving them enough energy to escape the planet's gravitational influence. This process removes atmospheric material even while the heated surface continues supplying new vapor. That creates a moving balance above the magma ocean. Material rises from the surface into the atmosphere, while radiation and stellar wind carry some of it away. We can think of the atmosphere as existing between these opposing flows, continuously renewed, yet continuously eroded. How stable that balance remains over geological time is still uncertain. If surface evaporation replaces atmospheric losses efficiently, a persistent rock vapor environment can survive. If escape consistently exceeds replenishment, the atmosphere may gradually become thinner. The star's long life adds another dimension to that uncertainty. As K2-141 slowly evolves, its luminosity will change, altering the amount of energy reaching the planet. Stellar evolution happens over immense timescales, far beyond a human lifetime, yet its consequences can reshape a planetary surface. Eventually, the star will leave its stable phase and become brighter as it evolves. For K2-141b, that changing radiation would intensify an environment already governed by extreme heating, atmospheric escape, and surface evaporation. The planet's history is therefore tied to the life of its star, with every stage of stellar evolution capable of rewriting the conditions imposed upon this scorched world. There may have been a time when K2-141b looked nothing like the world we know today. Its present environment seems permanent, yet planets inherit their histories from changing stars, shifting orbits, and long periods of planetary evolution. When K2-141 was young, it produced less energy than it does today. That difference could have mattered greatly for a planet already positioned close to the star. If K2-141b had reached its present orbit during that early period, its surface may once have remained below the temperatures required to melt ordinary rock. For a planet, even a temporary interval can become immense. Tens of millions of years would provide enough time for molten material to cool, crystallize, and form a solid crust. If water-bearing material had reached the planet during that era, some liquid water might have existed briefly beneath a less intense stellar environment. Yet there is an important uncertainty. We do not know exactly when K2-141b reached its current orbit. Planetary migration occurs through gravitational interactions with the young star system, and the journey inward could have lasted millions of years. During that migration, the planet would have passed through regions receiving very different amounts of stellar energy. You can imagine its history as a sequence of changing environments. Farther from the star, cooling would have been easier. Closer in, heating would have intensified. Each orbital position could have persisted for enormous spans of time, while the planet gradually lost the conditions associated with its previous location. Any evidence from those earlier eras would be extraordinarily difficult to recover. The present surface has been repeatedly transformed by extreme heating, evaporation, and the circulation of molten material. An ancient crust could have disappeared completely, melted back into the interior and becoming part of the material, now exposed to stellar radiation. Water, if it ever existed there, would have faced an even harsher fate. Intense ultraviolet radiation can split water molecules into hydrogen and oxygen. Hydrogen escapes readily into space, while the remaining oxygen can participate in chemical reactions with surface minerals. At sustained temperatures approaching 5,400 degrees Fahrenheit, long-term preservation becomes even less likely. Minerals that once formed under very different conditions could be melted, vaporized, or chemically altered until their original history became almost impossible to recognize. That leaves K2-141b with a strange limitation. Its present surface may tell us almost nothing about its earliest chapters. The planet could have passed through environments that no longer exist, leaving behind no intact crust and no obvious geological archive. For us, this changes how habitability should be imagined. A planet's location today is only one frame in a much longer story. Its migration, its star's evolution, and the timing of both determine which environments were possible. On K2-141b, any favorable interval would have existed against a rapidly changing background. The window may have opened briefly, then vanished as the planet moved inward and the young star grew brighter. What remains is a world whose present condition conceals a potentially very different past, buried beneath layers of material that have been transformed again and again by the same star that shaped its destiny. Every orbit brings K2-141b through the same gravitational field, yet the interaction never repeats in exactly the same way. The star pulls on the planet's interior, deforming both the solid rock and the molten layers beneath its surface. Gravity stretches the planet toward the star, creating tidal bulges that move as the planet travels around its orbit. Those bulges carry energy. They also carry angular momentum, the quantity that describes rotational and orbital motion. Because K2-141b completes an orbit in only 6.7 hours, the planet moves around its star far faster than the star rotates. That difference allows tides to transfer orbital energy into other forms, gradually reducing the distance between the two bodies. The change is extraordinarily small from one orbit to the next. You could watch the planet for a human lifetime and never notice its position shifting toward the star. Across millions or billions of years, however, tiny changes can accumulate into a very different orbit. There is a boundary known as the Roche limit. It marks the region where a star's tidal forces can become stronger than a planet's ability to hold itself together through gravity. K2-141b currently remains outside that boundary, but continued orbital decay could eventually carry it closer. Once a planet crosses the Roche limit, the process becomes dramatically different. Material at the planet's surface would begin responding more strongly to the star's gravity, allowing rock to escape from the planet itself. The loss would spread progressively inward, as tidal forces pulled material away. Some of that material could form a stream around the star. Given enough time, the debris could spread into a broad ring of vaporized and fragmented rock. We have already seen other planetary systems where close orbiting worlds appear to be losing material under intense stellar forces, offering clues about how such destruction can unfold. The exact lifetime of K2-141b remains uncertain. Tidal evolution depends on properties that are difficult to measure directly, including the internal structure of the planet and the rotation of its star. Current models do not place its final disruption within any humanly meaningful span of time. Still, the physics gives us a remarkable long-term picture. The planet exists in a state where its orbit, its interior, and its star remain gravitationally connected. Each revolution carries it through that relationship again, while tidal forces continue redistributing energy between them. For you, the change would be impossible to witness directly. One orbit passes, then another, and another. The planet remains apparently fixed in the darkness, even as gravity slowly reshapes its future across immense geological spans of time. Long before Earth developed oceans, continents, or a breathable atmosphere, its surface was dominated by molten rock. The young planet passed through a magma ocean phase, roughly 4.5 billion years ago, during the violent era when the Earth and Moon were taking their final forms. That ancient surface did not remain exposed forever. As Earth cooled, molten material crystallized into solid rock, while heavier elements descended toward the interior. Lighter materials remained closer to the surface, creating the broad chemical divisions that eventually shaped the rocky planet we know. Almost none of that earliest surface survives today. Geological recycling has erased much of the evidence. Rocks formed during Earth's magma ocean era were buried, transformed, and incorporated into the deeper planet, leaving scientists to reconstruct those processes indirectly. K2-141b offers something remarkably different. Its dayside remains hot enough to preserve a global ocean of molten rock, allowing processes similar to those that shaped early Earth to continue under direct observation. We cannot travel there and collect samples, yet telescopes can measure how minerals behave as they move between the molten surface, atmosphere, and colder regions. Those measurements reveal how different substances respond when a young rocky planet separates into layers. Iron is especially important. During Earth's early molten phase, dense iron moved downward and accumulated toward the center, while much of the silicate material remained above it. The same fundamental separation can be studied through the chemistry of K2-141b, offering another way to examine how rocky planets organize themselves. Silicon compounds provide another connection. On Earth, silicon dioxide became part of the solid crust, where it participates in long-term chemical processes involving water and carbon dioxide. One of those processes, called silicate weathering, gradually removes carbon dioxide from the atmosphere and helps regulate Earth's climate across immense stretches of time. K2-141b has no comparable planetary thermostat. Its silicon-bearing material can instead enter the atmosphere as vapor, where extreme heat keeps the chemistry fundamentally different from anything occurring across Earth's temperate surface. That distinction matters because planetary evolution depends heavily on where elements end up. A substance buried deep inside a planet can behave completely differently from the same substance exposed to an atmosphere or molten surface. For you, the comparison creates an unusual way to look backward through Earth's history. Our planet's earliest chapter disappeared beneath billions of years of geological change, while K2-141b continues displaying related physical processes today. The world around us is therefore more than an example of an extreme exoplanet. It provides a natural laboratory for studying the earliest stages of rocky planet evolution when heat, gravity, chemistry, and molten rock were still determining what a young world could become. Earth passed through that stage long ago. K2-141b remains within it. Before we group these worlds together, consider how recently the group existed. In 2009, Korot 7b, became the first confirmed rocky super-Earth found in such a tight orbit, with its dayside estimated near 4,200 degrees Fahrenheit. Its discovery established that planets with molten surfaces were more than theoretical possibilities. Since then, the catalog has widened. Kepler-10b added another scorched, rocky world, while 55 Cancri became one of the most closely examined examples. At 41 light-years away, it circles its star rapidly enough to offer repeated opportunities for observation, making changes in its atmosphere unusually accessible to telescopes. Recent observations have made 55 Cancri especially interesting. Its atmosphere had often been modeled as being dominated by carbon dioxide, yet observations from the James Webb Space Telescope indicate a more complicated composition, including substantial hydrogen. That result matters because the gases surrounding a molten planet can reveal what is happening beneath the surface. TOI 561b offers a different perspective. With an estimated age of roughly 10 billion years, it belongs to an ancient generation of rocky worlds. Its history stretches across more than twice the age of Earth, giving astronomers a chance to examine how prolonged stellar radiation and orbital evolution may reshape a planet over immense periods. Other candidates add further variety. HD 63433 deorbits its star at a distance where extreme heating remains possible, while the L98-59 system contains several small planets that help broaden our understanding of compact planetary systems. Each world occupies a different point within the larger family of highly irradiated rocky planets. But the catalog itself has a built-in bias. Transit surveys are particularly effective at finding planets with short orbital periods because those worlds cross their stars frequently. A planet completing an orbit in only a few hours can produce many detectable transits within a relatively short observing campaign. That means the worlds we know best may represent the most dramatic members of a much larger population. Less tightly bound planets could have intermediate temperatures, longer orbital periods, and atmospheres that behave differently, yet remain harder to detect. K2-141b has become especially valuable within this growing collection. Its measured density, detailed atmospheric modeling, and favorable observing geometry make it a useful reference point for testing theories about molten rocky planets. As new observatories examine more distant systems, the category itself is becoming easier to compare. The European Space Agency's Atmospheric Remote Sensing Infrared Exoplanet Large Survey Mission, planned for 2029, is designed to study the atmospheres of many exoplanets across a broad range of environments. For you, the emerging catalog changes the meaning of an extreme planet. K2-141b is no longer an isolated curiosity. It belongs to a growing family of worlds, each revealing a different way that rock, heat, atmosphere, and starlight can combine. A planet can disappear into the glare of its own star, leaving behind a signal almost too small to trust. For K2-141b, that signal may occupy only a few parts per million of the combined infrared light reaching the James Webb Space Telescope. We are trying to separate a whisper from an ocean of photons. The difficulty begins with K2-141 itself. Its surface is not perfectly uniform. Star spots, cooler regions created by magnetic activity, can alter the star's brightness and spectrum as they rotate across its visible surface. During an eclipse observation, those changes can resemble features belonging to the planet, creating a false atmospheric signature. Astronomers therefore have to understand the star before interpreting the planet. Repeated observations help establish how K2-141 varies naturally, allowing researchers to distinguish stellar behavior from changes that follow the planet's orbit. The task becomes a careful exercise in subtraction, where removing the wrong stellar pattern could erase the planetary signal along with it. Exoplanet science has learned this lesson through experience. Several early atmospheric detections, including proposed water vapor signatures, later became less convincing when stellar contamination was considered more carefully. A feature that appears to belong to a distant world can sometimes originate much closer to home, inside the star itself. For K2-141b, repetition becomes part of the measurement. Each time the planet passes behind its star, the James Webb Space Telescope can record another eclipse spectrum. Random variations should change from observation to observation, while a genuine planetary feature should remain tied to the planet's orbital position. With enough measurements, the persistent signal can gradually emerge from the changing background. This approach is statistical brute force in the best scientific sense. Resolution alone cannot solve every problem. Sometimes the only path toward greater certainty is to collect the same kind of evidence again and again. So, what would count as a detection? Not one attractive line in a spectrum. A convincing result requires a pattern repeated across observations, strong enough to cross a rigorous statistical threshold while surviving reasonable alternative explanations. The same principle reaches back to the planet's original discovery. Its transit was identified through a tiny recurring dip in starlight, appearing every 6.7 hours, while the observing spacecraft was already operating with only two of its four reaction wheels. Even then, astronomers had to separate planetary information from instrumental and stellar noise. Even the instrument itself must be treated as part of the equation. Detector behavior, calibration changes, and subtle thermal effects can introduce patterns that resemble astrophysical signals. So every observation carries layers of uncertainty that must be measured rather than assumed away. Today, the challenge has become finer. We are no longer asking only whether K2-141b exists. We are asking whether its atmosphere can leave a measurable fingerprint within the light of another star, and whether that fingerprint remains after every competing source of variation has been accounted for. The next generation of telescopes will approach K2-141b from several directions at once. Each instrument can reveal a different part of the planet's behavior, turning a distant point of light into a more detailed physical model. The James Webb Space Telescope is already central to that effort. By observing K2-141b through different infrared wavelengths, astronomers can search for changes in atmospheric chemistry and determine whether previously detected signals remain consistent across separate observations. Then comes the atmospheric remote sensing infrared exoplanet large survey mission, developed by the European Space Agency and planned for launch in 2029. Its purpose is broader than studying one world. The mission is designed to examine hundreds of exoplanet atmospheres, allowing K2-141b to be compared with planets experiencing very different stellar environments. Repeated observations could become especially valuable. If the rock vapor atmosphere changes with time, the pattern itself may reveal how material rises from the molten interior and escapes into space. A temporary increase in atmospheric density could indicate stronger surface evaporation, while a decline might reveal enhanced atmospheric loss. On Earth, we often measure a landscape directly. Here, we must reconstruct it from light. Future observations could estimate how rapidly rock vapor escapes, providing a way to determine whether the atmosphere is replenishing itself faster than it disappears. The extremely large telescope in Chile will add another layer of precision. Its primary mirror is designed to span approximately 128 feet, giving it an enormous light collecting surface. High resolution spectrographs could separate individual spectral features associated with sodium, silicon monoxide, and silicon dioxide. That distinction matters. A broad atmospheric signal can suggest that material exists, but individual spectral lines can reveal specific substances and their physical conditions. For you, the difference is subtle, yet scientifically enormous. Direct imaging remains much harder. K2-141b lies so close to its star that the planet is overwhelmed by stellar glare, preventing present instruments from resolving its surface directly. Future space telescopes, equipped with advanced coronagraphs, could potentially suppress that glare enough to study the planet's changing heat distribution. There is another possibility hidden within gravity itself. The star constantly deforms K2-141b through tidal forces, stretching its interior by an extremely small amount. Measuring that deformation could reveal how rigid the planet is and how its mass is distributed beneath the molten surface. That would connect the atmosphere to the interior. The surface chemistry, atmospheric loss, and internal structure could finally be studied as parts of one system. K2-141b therefore serves as more than a single target. Every successful technique developed around this planet becomes a method that can be applied elsewhere, helping astronomers compare an expanding population of molten rocky worlds across the galaxy. The search for life begins with a problem of definition. Before we can recognize a habitable planet, we must understand the worlds that fall completely outside that possibility. Around K2-141 star, the habitable zone lies far beyond the orbit of K2-141b. The inner boundary is roughly 40 times farther from the star than this molten world. That distance alone shows how profoundly its environment differs from the conditions required for stable surface water. Yet, studying such a planet remains useful. Every observation helps establish the boundaries of planetary chemistry, atmosphere, and temperature. Without those boundaries, an unfamiliar atmospheric signal could be mistaken for something extraordinary when ordinary geology provides another explanation. This becomes especially important when astronomers search for biosignatures, chemical patterns that might indicate biological activity. Oxygen and methane can be associated with life, but neither molecule belongs exclusively to biology. Volcanism, atmospheric chemistry, ultraviolet radiation, and mineral reactions can sometimes produce similar gases without any living organisms present. K2-141b gives scientists an opportunity to examine those alternatives directly. Its extreme environment allows researchers to study chemistry driven almost entirely by heat, radiation, and molten rock, creating a reference point for processes that could otherwise be mistaken for biological activity. Atmospheric escape provides another boundary. A rocky planet orbiting extremely close to its star is exposed to intense radiation and charged particles, which can remove atmospheric material over time. Measuring that loss helps scientists understand where the atmospheric conditions necessary for habitability begin to break down. The importance extends beyond one planet. Surveys from the Kepler Space Telescope revealed that short-period planets are common, suggesting that compact planetary systems are a normal outcome of planet formation. Some rocky worlds remain farther from their stars, while others migrate inward and enter environments where their surfaces can no longer retain familiar chemistry. That raises a deeper possibility. Earth may represent a successful combination of circumstances rather than the ordinary state of rocky planets. A planet needs more than a favorable distance. Its mass influences whether it can retain an atmosphere, while its interior determines how heat and volatile materials move through the planet. The type of star matters too, along with the timing of planetary formation, migration, atmospheric loss, and water delivery. Earth happened to preserve a remarkable balance. Its orbit allowed oceans to remain stable, its atmosphere developed within a suitable range, and its interior continued driving geological cycles for billions of years. The carbon cycle helped regulate climate, while the magnetic field provided additional protection against charged particles from the sunday. K2-141b shows how different the outcome can be. Change the orbital history, stellar environment, internal composition, or supply of volatile material, and the same basic ingredients of a rocky planet can produce something entirely different. When you look at Earth through that comparison, habitability begins to seem less like a default condition and more like a narrow intersection of possibilities maintained across immense stretches of cosmic time. Earth occupies a narrow address in space, one that has remained remarkably favorable for billions of years. At roughly 93 million miles from the Sun, our planet receives enough energy to keep surface water liquid across enormous stretches of geological time. That distance alone does not explain Earth's persistence. Jupiter also plays a role. Its immense gravity can alter the paths of incoming objects, sometimes redirecting large bodies away from the inner solar system. Farther below our feet, Earth's moon influences the planet's axial tilt, helping keep long-term seasonal patterns within a comparatively stable range. Neither circumstance was guaranteed when the planets formed. The Sun itself has been changing throughout Earth's history. As it gradually became brighter, Earth's climate remained within habitable limits through interacting geological processes. Silicate weathering removed carbon dioxide from the atmosphere, storing carbon in rocks and sediments, and helping moderate the planet's temperature over immense spans of time. Now place K2-141 beside that history. Its orbit lies roughly 40 times closer to its star than the inner edge of its star's habitable zone. The numerical difference sounds modest when reduced to a simple ratio, yet the physical outcome is enormous. One world supports oceans and ecosystems. The other maintains exposed molten rock beneath relentless stellar heating. Our galaxy may contain hundreds of millions of rocky planets positioned where surface water could potentially persist. Estimates derived from planetary surveys suggest roughly 300 million such worlds may exist within the Milky Way, although the number remains uncertain because many planets are still beyond current detection capabilities. That estimate becomes more striking when placed beside the galaxy's enormous stellar population. The Milky Way may contain hundreds of billions of stars, meaning potentially habitable, rocky planets form only a small fraction of the planetary environments available. Most worlds occupy conditions that make surface water unstable, unavailable, or impossible to maintain for long periods. K2-141b belongs to that larger population of extreme outcomes. Its molten surface is not an isolated accident in the universe, but one possible result of planetary formation, migration, stellar radiation, and atmospheric evolution. Yet, Earth remains the world we know most intimately. Its oceans, atmosphere, magnetic field, interior, and orbital position emerged from a particular sequence of events that could have unfolded differently. A small change in any one of those circumstances might have produced a planet with a very different surface. When we compare Earth with K2-141b, the contrast becomes more than a difference between two planets. It becomes a measure of how many conditions must align for a rocky world to remain habitable across billions of years. Earth may be unusual. The universe has many more ways to make a barren world. 202 years is the age of the light reaching us from K2-141b today. When those photons began their journey, Earth was in 1824. Steam power was reshaping industry, and the existence of planets beyond our solar system remained unknown. Across that enormous interval, K2-141b kept circling its star. The planet completed roughly 263 million orbits before the light arrived here. For us, the number is almost impossible to picture. For the planet, each orbit was simply another repetition of the same astronomical mechanics. Meanwhile, humanity changed almost beyond recognition. We moved from steam engines to spacecraft, from handwritten star charts to instruments capable of separating faint wavelengths of infrared light. Yet the distance itself remains almost untouched by our technological progress. Voyager 1, the most distant human-made object ever launched, has traveled roughly 165 astronomical units from Earth after decades in space. K2-141b lies about 1.3 million astronomical units away. At Voyager 1's present speed, reaching that planet would take roughly 40,000 years. There is no practical journey waiting between here and there. We cannot land a probe, collect a sample, or place an instrument above its surface. Everything we know must cross the distance as information carried by light. That changes what observation means. The molten ocean, the mineral winds, and the falling rock described by planetary models were never photographed from nearby. Instead, astronomers read subtle changes in starlight, separating planetary signals from the much brighter star that surrounds them. A transit reveals one kind of clue. An eclipse reveals another. Spectral shifts reveal chemical fingerprints, while changes in brightness can expose differences between the planet's illuminated and hidden hemispheres. Each measurement contributes another constraint, narrowing the range of possible explanations. Even the planet's atmosphere is therefore reconstructed indirectly. Scientists combine observations with thermodynamics, fluid dynamics, atmospheric chemistry, and models of stellar radiation. When several independent methods point toward the same physical picture, confidence grows. But confidence is not the same as direct contact. A model can be remarkably successful while still containing uncertainty. The temperature distribution may be estimated within a range. Atmospheric circulation can be simulated from known physics. Mineral behavior can be predicted under extreme pressures and temperatures, yet no human instrument has stood there to verify those predictions firsthand. That distinction matters because science is built around the boundary between what we observe and what we infer. K2-141b offers an extraordinary example. From a tiny change in distant starlight, we can reconstruct processes unfolding across an entire alien world. You are looking at evidence gathered from across interstellar distance. The planet itself remains unreachable, while its light arrives with information embedded inside every subtle variation. That is the strange advantage of astronomy. We do not need to touch a distant world to learn about it. We need only learn how to read the light that survives the journey. For billions of years, K2-141b existed without a witness. Its star rose over the same hemisphere. Its surface responded, and its orbit continued around an otherwise ordinary star. No instrument measured the heat. No telescope recorded the changing minerals. No distant observer knew the planet was there. Across those immense spans of time, the world followed its physical laws without interruption. Rock evaporated from the dayside, entered the atmosphere, and traveled toward colder regions above the planet. Some of that material eventually condensed and returned to the surface. The process repeated beyond any human measure, then repeated again. On the night side, mineral particles accumulated layer by layer. Each deposit became part of a geological record, although there was no one present to interpret it. The surface carried evidence of planetary processes that had no audience. Above it, the stars of the Milky Way remained scattered across the darkness. K2-141b had no moon illuminating its surface, no spacecraft passing overhead, and no civilization wondering what might exist there. For billions of years, the planet simply existed. Its winds crossed the boundary between opposing hemispheres at thousands of miles per hour, driven by the enormous difference between regions receiving intense stellar energy and regions receiving almost none. The atmosphere carried minerals across that boundary again and again. Below those winds, the magma ocean continued circulating. Heat moved through molten rock, chemical components separated and recombined, and material rose from deeper layers toward the surface. Nothing needed to observe these processes for them to continue. That distinction matters. Physical events do not wait for recognition. A star does not become brighter because someone measures its light. A planet does not change its orbit because someone gives it a name. Then, in 2017, a telescope watching a distant star detected something unusual. The star's brightness dipped at regular intervals, revealing that an unseen planet was crossing in front of it. That discovery connected an ancient world with a very recent observer. The planet had already existed for billions of years before humanity noticed it. We arrived unimaginably late to the story. By the time its light reached Earth, entire human civilizations had risen and disappeared. Languages had formed, changed, and vanished. Cities had been built, abandoned, and buried beneath later generations. Yet the same planet continued its orbit. Now, when you look toward that distant system through a modern telescope, you are receiving information carried across 202 light years. The photons began their journey long before anyone on Earth knew what they represented. That makes observation an unusual kind of encounter. We cannot touch K2-141b, alter its surface, or hear anything from its atmosphere. We can only collect the light that reaches us and reconstruct the world hidden within it. The planet itself remains indifferent to our attention. Its molten surface continues moving. Minerals continue traveling through its atmosphere. Its orbit continues around its star. But the meaning of those events has changed for us. For the first time in billions of years, another world has become part of human knowledge. A planet that once existed beyond every human map now occupies a place in our understanding of how worlds form, change, and endure. K2-141b was there before we knew to look. Now, we know where to look. There is a strange boundary between existing and being known. K2-141b crossed that boundary only recently, after billions of years of planetary history had already passed. For most of its existence, nothing on Earth knew it was there. No human mind had imagined its orbit, calculated its temperature, or wondered what its surface might contain. The planet continued through every stage of its cycle without becoming part of anyone's understanding. That distinction becomes especially interesting when we consider what observation actually means. In quantum physics, measurement can affect a system under certain conditions. At planetary scales, however, our telescopes do something very different. They collect information. K2-141b does not respond to being observed. Its star continues heating the day side. Its atmosphere continues carrying vaporized minerals. Gravity continues shaping its orbit. Our attention changes none of those processes. And yet, observation still accomplishes something profound for us. Once we identify a distant world, we can give its physical history a place within human knowledge. We can describe its atmosphere, model its circulation, estimate its interior, and compare its evolution with other rocky planets. A name becomes a doorway. K2-141b is no longer merely a collection of physical events occurring far away. It becomes an object that can be studied, discussed, questioned, and understood. Carl Sagan once described humanity as a way for the cosmos to know itself. On this planet, that idea becomes remarkably concrete. Matter on Earth has developed into organisms capable of receiving photons from another planetary system and extracting meaning from their tiny variations. Think about what that requires. A distant star emits light. Some of that light interacts with a planet. A fraction continues across interstellar space. Centuries later, detectors on Earth register minute changes, and human beings translate those changes into a picture of another world. The chain is extraordinary, yet nothing in it requires K2-141b to participate. That is where philosophy begins, because science can describe the physical process but cannot decide whether awareness gives existence a deeper significance. Does a world become more meaningful when someone understands it? Or is understanding valuable only to the observer? There is no measurement that settles this. We can only recognize the contrast. K2-141b follows physical laws without intention, while Earth-produced beings capable of wondering about those laws. One world is dominated by molten rock and extreme radiation. The other contains oceans, forests, cities, and mines capable of looking outward. Across 202 light years, those worlds remain connected by information. You are part of that connection now. When you learn how K2-141b behaves, a tiny portion of an otherwise inaccessible planetary history becomes present within a human mind. The planet itself remains unchanged, but the universe has become slightly larger inside our understanding. K2-141 will outlive almost every era humanity has ever known. Its K-dwarf star is expected to remain stable for tens of billions of years, far beyond the present age of the universe. That longevity changes the meaning of time here. Our universe is about 13.8 billion years old. Yet K2-141 may continue shining for another 20 to 70 billion years, depending on the details of its stellar evolution. Consider the distance between those timescales. 5 billion years from now, our sun will have exhausted much of its hydrogen fuel and entered the final stages of its stellar evolution. Earth may no longer resemble the world we recognize today. K2-141b will still be orbiting its star. Its surface will continue receiving intense radiation. Molten rock will continue circulating beneath the atmosphere. Mineral vapor will continue rising from the hottest regions, while atmospheric currents carry that material toward colder parts of the planet. The same physics keeps operating. For us, billions of years suggest enormous change. Continents move, species disappear. Stars are born and die. Civilizations appear for a brief interval, then vanish. On K2-141b, however, the dominant processes can remain remarkably persistent across geological ages. A billion years ago, the planet may have looked broadly similar to its present state. A billion years from now, our models suggest much the same pattern could remain, provided the star's evolution has not significantly altered the system. That stability makes human history look almost impossibly brief. The earliest stone tools appeared millions of years ago, while modern astronomy developed within only the last few centuries. Even the entire history of civilization occupies a tiny fraction of the planet's ongoing existence. You can compress our story into a moment. K2-141b has no need for such compression. Its orbital cycle repeats every few hours, while its larger geological pattern persists across immense stretches of time. Each orbit is brief compared with its lifetime, yet countless orbits accumulate without fundamentally changing the system. The planet therefore offers another perspective on what we call permanence. Nothing in astronomy is truly permanent, because stars evolve and orbits change. Stability simply means that change can become so gradual that an entire civilization passes without visibly altering the system. Eventually, even K2-141 will evolve. Its brightness will change as its internal fuel is consumed, and the planet's environment will respond to that transformation. But those changes belong to timescales almost beyond human imagination. For now, the star continues burning. The planet continues circling, and our entire species occupies only a narrow interval between those two facts. Most of the universe has no awareness of passing time. Stars burn, planets orbit, galaxies move, and matter changes according to physical laws without needing anyone to notice. K2-141b fits naturally within that immense pattern. Its existence does not require a witness, explanation, or purpose, yet we are here to observe it. That is the unusual part. A world can burn for billions of years without anyone asking why. Humanity, given only a few thousand years of recorded knowledge, has already learned to look across unimaginable distances and recognize such a world. Against cosmic time, our presence is brief, but within that brief interval, we can notice the universe happening. Across the observable universe, the numbers become difficult to hold in the mind. Estimates suggest roughly 2 trillion galaxies, each carrying its own history of stars, planets, collisions, and change. Within our Milky Way alone, perhaps 200 to 400 billion stars illuminate an enormous population of worlds. Some are frozen beyond recognition, others are scorched by their stars. Many may have lost their atmospheres entirely. Some orbit so closely that tides tear them apart, while others drift through darkness with almost no warmth available at their surfaces. K2-141b belongs among these worlds, shaped by conditions that leave no room for life as we know it. And that is where the scale of this story changes. The unusual thing is not the planet. The unusual thing is us. A world of molten rock can exist for billions of years without producing a question. Its minerals obey gravity, its atmosphere responds to heat, and its orbit follows the geometry of the system. None of those processes requires understanding. Then, on another world, matter became organized differently. Atoms formed molecules. Molecules became chemistry. Chemistry became biology. Biology developed nervous systems, memory, language, mathematics, and instruments capable of gathering faint signals from distant stars. Eventually, that chain produced you. You can look at a point of light and ask what exists around it. You can measure a tiny change in brightness, compare it with physical models, and reconstruct a planet that no human being could ever visit. That ability is remarkable precisely because it is physical. There is no separate substance called awareness that must be added to matter. The atoms in your body obey the same fundamental laws found throughout the cosmos. Yet, arranged through an extraordinarily long history, those atoms became capable of studying their own surroundings. K2-141b cannot return the observation. It has no telescope. It has no archive. It has no mechanism for wondering what lies beyond its atmosphere. Across 202 light years, there is another rocky world carrying oceans, continents, organisms, and minds. The planet cannot know that any of them exist. We can know that it exists. That difference may be the most important fact left by this journey, not because it gives the universe a purpose. Science cannot establish such a purpose, and not because observation makes distant planets conscious of us. They remain governed by physics, whether we watch them or not. The significance lies somewhere more concrete. We are matter that can construct an explanation for other matter. We can take ancient light, pass it through instruments, and extract information about temperature, chemistry, motion, and structure. We can turn those measurements into models, then test those models against new observations. For a brief moment in cosmic history, one small species has become capable of doing this. The galaxy does not need our questions, but our questions exist within it. And when we look toward K2-141b, we are seeing more than another distant planet. We are seeing evidence that the universe can produce worlds, stars, chemistry, life, and eventually something capable of looking outward and asking what any of it means. When this recording ends, K2-141b will continue its orbit. Nothing there will pause. The molten surface will continue moving beneath its atmosphere, while mineral vapor rises, cools, and returns across the darker hemisphere. Winds will continue tracing the boundary between permanent day and permanent night. The planet will follow the same physical laws it followed before anyone on Earth knew its name. Our attention has no measurable effect on any of this. That is part of what makes the act of looking so strange. We spend years building instruments for distant worlds. We collect photons that have crossed interstellar space for generations, then turn those faint arrivals into measurements, models, and explanations. Eventually, those explanations become part of human knowledge. The planet does not receive that knowledge. We do, and perhaps that is enough. There is something unusual about being alive during an age when distant worlds can become objects of study. You can sit beneath an ordinary sky and consider a planet hundreds of light years away, even though no human hand has touched its surface. The distance remains enormous, yet information crosses it. A telescope gathers light. Computers separate patterns from noise. Scientists compare those patterns with the predictions of physics. Slowly, something that once had no place in human thought becomes familiar enough to describe. K2-141b becomes a name, then a world, then a place with weather, geology, chemistry, and a history. That transformation happens entirely inside us. The planet itself requires none of it. Its molten rock does not need a witness. Its atmosphere does not need a story. Its orbit does not need a purpose assigned by a distant observer. But we are observers. We are the kind of matter that records what it encounters and asks what those records mean. We construct telescopes larger than houses, send instruments beyond our planet, and preserve observations for people who may study them decades after we are gone. There is no guarantee that every question will be answered. Some never will. A human lifetime is too brief for many astronomical processes. Civilizations change while stars continue burning. Instruments become obsolete while planets remain in orbit. The people who make a discovery may disappear long before the light they studied stops arriving. Still, we keep looking. Perhaps that persistence is one of the clearest descriptions of what we are. K2-141b does not become more important because humanity noticed it. Its existence was never waiting for recognition. The significance belongs to the observer, to the decision that this distant world was worth understanding. You can call that curiosity. You can call it science. You can simply call it looking. Whatever name we choose, the act remains remarkably human. We take a brief interval between birth and disappearance, then use part of it to understand something that existed long before us and will continue long after us. Across 202 light years, a planet continues its ancient cycle. Here we are listening, and for a little while we are looking back. The journey can end here. K2-141b remains far beyond the reach of any human traveler, continuing its ancient orbit around its star. Its surface remains a vast ocean of molten rock, heated beyond anything found naturally on Earth today. There is nothing you need to do with that knowledge now. The planet will continue without us. Its atmosphere will rise from the glowing surface, move across the planet, cool above the darker hemisphere, and return toward the molten depths. The cycle requires no observer. It simply follows the laws that have governed this distant world for ages. And here you are somewhere else entirely. Perhaps the room around you has grown darker. Perhaps the only light nearby comes from a small screen, fading as the documentary reaches its final moments. For a little while, we have traveled across an impossible distance without moving at all. We followed light. We followed evidence. We followed the faint signatures left by a world that no human being has touched. Now there is nothing more to solve. K2-141b is still there, 202 light years away. Its star continues to rise and fall across the planet's locked hemispheres. Rock continues to vaporize. Mineral clouds continue to move. Condensed material continues returning to the surface. The universe does not stop when we stop watching. That may be the simplest place to leave the story. You are here, on a small world with breathable air, liquid water, and temperatures gentle enough for your body to rest. Your surroundings may seem ordinary because you have lived among them all your life. But ordinary is a matter of perspective. Somewhere far away, an entire planet exists under conditions almost impossible to imagine from a bedroom, a chair, or a bed. Its environment is shaped by tremendous heat and relentless gravity, yet it remains stable across stretches of time that make human history seem almost weightless. You do not need to carry that scale with you tonight. You can let it remain out there. The stars can remain where they are. The distant planet can continue its orbit. And for this moment, nothing is asking anything from you. There is no equation to complete, no observation to record, no distant world that needs to be understood before you can close your eyes. The universe will continue unfolding whether we are awake to see it or not. For now, you can simply remain here, beneath your own atmosphere, on your own small world, sharing the same universe as that distant ocean of fire. K2-141b keeps burning. You can rest. Let the distance disappear. Let the numbers fade. Let the story become only a distant point of light. And for a little while, you do not need to go anywhere.